Hi, everyone. My name is Ed Miller. I'm a senior engineer at ARM, and I also volunteer as a developer for the Bear ID project. And I'm an AWS machine learning hero. Thanks for joining me today for this talk about how to utilize Amazon Rekognition for low code, no code computer vision applications, and how the Bear ID project utilizes recognition and custom labels for wildlife conservation applications. Today, I'll provide an overview of the Bear ID project in Bearcam Companion, how Bear ID uses recognition for detecting bears and integrating it with the Bearcam Companion. And then we'll discuss how to create a new model using custom labels. And finally, I'll provide some links and resources and wrap things up. Bear ID Project is a nonprofit collaboration between ecologists and software engineers. We develop non-invasive methods for monitoring wildlife, namely bears. Bear ID is a machine learning based face identification application that we developed for researchers to use with their fieldwork. It identifies bears from photos, videos, and camera traps. Bear ID was initially inspired by Explore.org's bear cams. In an attempt to harness the citizen scientists that watch these cams, we built the Bear Cam Companion. In previous talks and blogs, I described a little bit about our aims and how we built the application using AWS Amplify. The end goal is for automatic identification using human in the loop machine learning techniques. The application automatically grabs snapshots from explore.org and identifies the bears. The users watching the cam can use the application to review or label bear identifications. The identifications are processed to generate a data set for training an identification model. And then the new model is deployed back to the application. So far, we have only the automatic detection and still rely on users to identify the bears. So let's talk more about detecting bears. A key step in the application is to find the bears in the images. Our previous Bear ID model only detected bear faces. For Bearcam Companion, we want to be able to detect the complete bear. At the start, we didn't have a labeled data set to train a bear detector. However, Amazon Rekognition can detect bears and many other objects. This example shows a snapshot from an Explore image in the Rekognition demo console, and you can see it detects a bear at 95.6% accuracy. Rekognition can be easily integrated with an Amplify application. First, you can add Rekognition to the project using Amplify add predictions. Update the backend by doing an Amplify push. And then from your application, you send images to Rekognition with predictions.identify. Then you can parse the results and do whatever you need with them. For the Bearcam Companion, we really want to automate this flow. So we set up an event bridge to fetch a frame, event bridge rule to fetch a frame from explore.org every 10 minutes or so. When the new image is loaded into the images table, it fires off a Lambda function. The Lambda function for each inserted image will send it to Rekognition and parse the results, and then finally store the results back into the object table. In the Lambda function, we parse event records and loop through the inserted images. I have a function called process image for each new image, which I call. And you can provide optional parameters like minimum confidence level, as well as pointers to the image itself in an S3 object. And then you can call Rekognition.detect labels to actually invoke recognition and get the return response. The recognition response is a JSON object. There's an excerpt here on the right. For our needs, we only care about the object detections, which are shown by the bounding boxes, which is shown in the excerpt on the left. There's a bounding box indicating a bear of 95% confidence, the dimensions, the locations of the bounding box information. Here's an example function that we use to parse the response. It loops through the labels. If there's a bounding box, it returns that information. And then the calling function can use those results, in this case, to write the info to an objects table in DynamoDB. While Rekognition supports several use cases very well, it isn't perfect for every application. For image labeling, it supports more than 3,000 labels and nearly 300 objects. I expect bears is not a big portion of the training data, especially in all the various poses that we see from the webcam. Sometimes it mislabels bears, as you can see here. There are some dogs, there are some kangaroos, there's a few bears that don't have detections at all. So we'll talk in a minute about improving the model. First, let's see Rekognition in action in the BearCam Companion. So here's the main page of the BearCam Companion application. Any user can log in and view any of the images and add their identifications to the bears if they know them, or they can just review the existing labels to see what other CAM viewers have identified. As a site admin, I can also view a list of images that are being downloaded from Explore as the most recent snapshots. So if I find an image here that I find interesting, although currently they're all very similar, I can go ahead and save this image, and it will automatically trigger Rekognition to do inferencing on the bear detection. So if I go back to the home screen, I can see this image has been added to the list, and I can see that some of the bears have not been labeled. I have an editing capability built into the application. I can see here that there was an extra box labeled as a kangaroo, and this bear was labeled as a dog instead of a bear. So we can fix that label. And when we return back to the image view, that bear also has a box around it. So now you can see the updated labels. So I don't really want to spend so much time manually adjusting labels. For most machine learning, the next step would be to fine-tune your model. You can essentially fine-tune Rekognition using Rekognition custom labels. You do this to make it better at specific objects like bears, or for defining new objects like a product, a logo, or really it depends on whatever your application needs are. You can create a custom labels project in AWS Console. Once you have a project, you can create the data set. You can pre-split the data set into train and test, or you can let custom labels do it for you. There are several ways to import the images. In my case, I imported it as manifest file. Manifest files are typically come from SageMaker Ground Truth, but since I already have been collecting and updating the labels in the BearCam Companion, I generated my own manifest file using a Python script to extract the data from DynamoDB objects and image tables with the links to images on S3. And then I uploaded this manifest file to S3 and provided the link on the form. I had already pre-split this data set, 80% for train, 20% for test. And from my initial application implementation last year, I had 2,486 training images and 605 test images in this set. Many of these images have multiple bears, so this should increase our number of training options. You can also use custom labels interface to add labels directly into your data set. But since my manifest already had these included labels, I can just view them using the interface. Alternatively, we could have used ground truth for a larger labeling job, especially if we want to farm them out to a broader workforce. I did find a few errors in my data set, things that I must have missed while using the application initially, like this bear on the left where there's a missing box. So I adjusted the labels in the custom labels interface directly, since there were only a few. And when the data set's ready, you're ready to start training. This can take several minutes to many hours, depending on the data set and how similar it is to the existing models. Once it's completed, the model's ready to run. But first, let's take a look at the model performance. Clicking on the model, you'll find per label performance information, such as F1 scores, precision, recall, and the assumed thresholds used for those numbers. In my model, there's only one label bears, but if you had more labels, they would all appear here with their individual scores. You can view the test results to see performance on each individual image in the test set. Here you can quickly filter for errors to see where your model may need improvement. For example, in this false negative, the model missed one of the bears, showing correct bears in green and the incorrect or missed bear in red. For a false positive example, here the model labeled some branches downstream in the water as a bear. Although I do note that as these bears get quite distant, it is very difficult to discern them from other objects in the water. And occasionally you might even find errors in your test set itself. In this case, there were two bears on the shore that I had not identified that custom labels did identify correctly. So I would need to fix these labels and then rerun the tests so I can get a more accurate result. Once you're happy with the model, you can start and stop the model in the console. The example code for the model usage is provided. You can choose how many instances to create, how many instances to increase your throughput, and you're basically charged for instance hours or how long you use how many instances. Turns out this isn't a great fit for the Bearcam Companion. Right now, I'm only running about six inferences per hour. And so spending uptime on a server for an hour is probably not the best use of my time or my credits. For now, because of our low usage, we would prefer an on-demand model for bear detection. So one of the next projects is to train a bear detector using Amazon SageMaker. And we'll use that as an on-demand, probably in a Lambda function, but we're going to leave that for another time. So here's some links about the project, the services we discussed, and you should be able to get these links when the slides become available, which should be soon. And to wrap up, in this talk, we learned how to integrate recognition with the Amplify application. We learned how to automate detection with Lambda and recognition. And we learned how to create more specialized detectors using recognition custom labels. So it looks like we've reached the end of the presentation. Thanks for joining me, and I'll see you next time.